Hi everyone and welcome to the presentation of the paper Evaluating Susceptibility of VPN Implementations to DOS Attacks using Adversarial Testing. My name is Fabian Streuner and I've been working on this project with Joel Wanner and Adrian Perrick. Virtual private networks enable secure communication over the internet and are widely used by corporations as well as by private individuals. Often VPNs serve as the main access point for protected services and resources. For consumers, there exist various different VPN protocols and implementations, including WireGuard, IPsec, OpenVPN, Cisco's AnyConnect, and so on. If you want to know how well the different implementations perform, you can look at one of the many published benchmarks out there. Commonly, these benchmarks consider a setup in which a VPN client connects to a VPN server over the internet. And they measure throughput, latency, CPU utilization, and so on. These are all really important metrics to ensure that an implementation meets a deployment requirement. However, such benchmarks don't account for an attacker in the setup. And therefore, the question arises, how resilient are VPN implementations against an attacker? In our research, we look at 4 VPN implementations: WireGuard, the IPsec-based strongSwan VPN, OpenVPN, and Cisco's AnyConnect. And we evaluate their resilience against certain DOS attacks. To get started, I would like to give a brief overview of the different VPN protocols and common DOS mitigation mechanisms. A VPN protocol can usually be divided into 2 parts, the handshake and the data transport part. During the handshake, the client and server authenticate each other and generate keys. With the generated keys, further data transport between the peers is then authenticated and encrypted. During the handshake, significant processing resources are required and memory is allocated. Therefore, an attacker which floods the server with handshake requests might be able to overwhelm the server and exhaust its resources, causing a denial of service. VPN protocols and implementations mitigate such attacks in various ways. For example, source blocking and rate limiting in combination with address binding cookies are common defense mechanisms. Some protocols also make use of pre-share keys to be protected from external adversaries. Implementations often try to prioritize the processing of already authenticated traffic over unauthenticated traffic and parallelize work to increase not only performance but also DOS resilience. IPsec-based VPNs commonly use the IKv2 protocol for the handshake. To mitigate resource exhaustion attacks, in particular memory exhaustion attacks due to a flood of initiation requests, implementations enforce IP-based limits. However, such limits are not effective against an attacker which can spoof its IP address. To defend against spoofing attacks, IKv2 provides an address binding cookie mechanism. Also, the WireGuard protocol applies IP-based rate limits for initiation requests in combination with a new variation of the cookie mechanism to be protected against spoofing attacks. Additionally, WireGuard also leverages the peer's public keys, which have to be shared before a connection can be established. During the handshake, packets must contain a message authentication code called MAC1, which is calculated using the receiver's public key. Therefore, an attacker which does not know the server's public key cannot generate valid packets for the server. The protocol used by OpenVPN is more or less TLS over UDP. To protect the TLS handshake, multiple mechanisms are provided. Firstly, there is TLS crypt. With TLS crypt, all peers share a secret key and use this to authenticate and encrypt all the TLS packets. An attacker which does not know this key will not be able to generate valid TLS packets. However, this approach does not scale well. Then in case the key is leaked, a new key would have to be distributed to all peers at once. To address this issue, OpenVPN came up with TLS crypt version 2. With TLS crypt version 2, each client can have a separate key to authenticate and encrypt the TLS packets. Each client also gets its key encrypted with the server's key. This wrapped key is then sent in the initiation packet to the server, such that the server can obtain the client's key and does not have to keep a list of all the client keys. Simplified, Cisco's AnyConnect SSL-based VPN first establishes a TLS connection and then a DTLS connection. Since the TLS connection runs on top of TCP, an attacker could perform a TCP SYN flood to overwhelm the server. To mitigate this, the implementation makes use of SYN cookies. Similarly, the DTLS handshake is protected with a cookie mechanism. So knowing that all protocols have DOS mitigation mechanisms in place, we would like to evaluate their effectiveness in the different implementations. For our evaluation, we used a setup consisting of 3 machines connected over a 40 gigabit network. 2 machines were running the VPN implementations. One was the VPN client, which connected to the other machine, the VPN server. The third machine was the attacker, which flooded the VPN server with packets. During the flooding attacks, we measured the throughput between the VPN client and the VPN server over the VPN connection. We also measured the time required for the VPN client to establish a connection to the server. With these measurements, we were able to evaluate the resilience of the different VPN implementations against certain DOS attacks. Important to note here is that the device under test, the VPN server, is a commodity server equipped with 2 Intel Xeon CPUs, providing a total of 72 logical cores. As we are working with a multi-core system, receive-side scaling starts to play an important role. RSS is a mechanism that distributes the processing of received packets among multiple cores. Typically, the hash over the 4-tuple IP address, TCP and UDP ports determines the core to which a packet is forwarded. Concerning the flooding attacks, we therefore considered 3 different flow configurations. In the single flow attack, the attacker always uses the same IP address and port numbers. RSS then maps all attack packets to the same core, which is likely a different core than the core which processes the client packets. In the multi-flow configuration, multiple IP addresses and port numbers are used, such that RSS distributes the attack packets among all the cores of the VPN server. The third configuration that we have considered was the client flow configuration. In the client flow configuration, the attacker uses the same IP address and port number than the client does. Therefore, attack packets and client packets are mapped to the same core. At first, let's take a look at WireGuard. On this slide, we see how well WireGuard handles a flood of handshake initiation requests. The x-axis represents the rate at which the attacker floods the server. On the y-axis, we have the measured throughput and the measured connection time. The plots show that the throughput between the VPN client and the VPN server is denied with roughly 1.6 gigabits per second of attack traffic when sent over multiple flows. With the client flow configuration, about 600 megabits per second of attack traffic are already sufficient. To consistently deny connection establishment, roughly 20 gigabits per second are required. To put these measurements into a context, we also established a baseline by flooding the server with generic UDP packets of the same size. By sending generic UDP packets to the same port, we can see the processing limitations of the VPN server's hardware and kernel. The plots clearly show that the hardware is definitely capable of handling higher attack rates without drastic impacts to the VPN's performance. To understand how a flood of handshake initiation packets can have such a significant impact on the VPN's performance, we have to take a look at WireGuard's implementation. In short, WireGuard tries to achieve high performance by utilizing all available cores on the system. When a packet is received, RSS forwards it to a specific receiver core, where the packet is processed by the kernel and then parsed by WireGuard. If the packet is a handshake packet, it is added to the handshake packet queue and then processed by one of the workers spawned on all the other cores. When we profile the server by flooding it with initiation requests over multiple flows, we observe that the 72 cores spend up to 90% of the runtime in spin locks. These spin locks are in place to coordinate the enqueuing and dequeuing of the attack packets to and from the handshake packet queue. Therefore, the big number of threads accessing the same data structures seems to be the cause of the performance problems. With the client flow configuration, the profiling revealed that the receiving core is the main bottleneck. The receiving core spends a significant portion of the time waking up the workers on the other cores. This indicates that the multi-threading is not optimized with respect to malicious traffic. Instead of just flooding the WireGuard server with initiation requests, we also looked into automating the exploration of other flooding attacks. We implemented an algorithm that expects a list of packets which can be used to flood the server, and then looks for the packet mix which disrupts the VPN connection with the least amount of attack traffic as possible. We applied this to WireGuard and gave all kinds of WireGuard packets to the exploration algorithm. This includes the 3 Handshake packets and some data transport packets. The exploration algorithm then found a packet mix which disrupts the VPN's connection with just 750 megabits or 300 megabits per second of attack traffic in the multi-flow or the client flow configuration respectively. The mix clearly favors Handshake packets over data packets. Especially interesting is that the cookie response packet seems to be the most important packet in the mix. Since the cookie response packet is the smallest Handshake packet, this indicates that the Handshake packet rate is a significant factor of this attack's effectiveness. Coming now to the evaluation of the IPsec based strongSwan implementation. When we flood the server with initiation requests, we see that an already established connection cannot be that easily denied. On the other hand, connection establishment is denied with about 75 megabits per second of attack traffic, independently of the flow configuration. That only the connection establishment is affected by the attack can be partially explained by looking at the implementation. With strongSwan, the data packets are processed in the kernel. On the other hand, the Handshake packets are processed in the user space, where one thread receives all packets and distributes some processing among other cores. A flood of Handshake initiation packets is able to overwhelm the receiving thread and denies other clients from successfully establishing a connection to the server. The data transfer, on the other hand, is not impacted. Now to the evaluation of OpenVPN. Our evaluation revealed that roughly 100 megabits per second of initiation packets are sufficient to overwhelm the OpenVPN server independently of the attack flow configuration. Throughput as well as connection establishment can be denied. Also, the different TLS protection mechanisms do not have a significant effect on the attack's impact. OpenVPN's implementation runs just on a single core and processes Handshake packets as well as data packets. Therefore, a flood of Handshake packets also impacts the processing of data packets. Cisco's AnyConnect offers an IPsec-based and an SSL-based VPN solution. First, we'll look at the DOS resilience of the IPsec implementation. Just as for strongSwan, we see that flooding the server with initiation requests mainly affects connection establishment. 50 megabits per second are sufficient to deny the client from connecting to the VPN server. To deny throughput, roughly 5 gigabits per second of attack traffic are required. In contrast to strongSwan, we see that already a flood of generic UDP packets over multiple flows significantly impact the VPN's functionality. Therefore, we also flooded the server with minimal sized UDP packets. And we see that already 300 megabits per second of attack traffic is sufficient to deny throughput of an already established connection. The evaluation of the SSL-based VPN reveals that also here minimal sized UDP packets can be used to overwhelm the server. With 50 megabits per second of attack traffic, an already established connection can be denied, while 200 megabits per second of attack traffic are sufficient to consistently deny connection establishment. So coming to the conclusion, how resilient are VPN implementations against DOS attacks? Our research has revealed that with little amount of attack traffic, essential functionalities of widely used state-of-the-art VPN implementations can be denied. Further, and sadly I didn't have time to go into that, we found multiple vulnerabilities. These include a vulnerable cookie mechanism and exploitable default configuration in strongSwan. For OpenVPN, we also found a single packet DOS attack. All findings have been reported to the developers during the year 2021. Overall, we think that there is a lack of adversarial tests and benchmarks. For the future, we hope that more adversarial tests and benchmarks will motivate the development of software with high resilience against DOS attacks.